these notes up, and I think I have it. There we go. So the math of change. If the world were run by machines, maybe calculus would be necessary. What am I talking about? If there was a machine that was in charge of speeding up and slowing down your car, maybe the rates wouldn't be quite as varying. Maybe all motion would be linear. However, for anyone who does drive a car, we don't perfectly speed up at a constant rate or slow down. And as we already talked about, we don't move at a constant rate. And that's just with driving. The math of change. Quantities are changing. And quantities are changing in dynamic ways, not in static ways. Static basically is boring. Dynamic is a bit more exciting. So that's not exactly the math definition. That's just kind of like the English definition, if you want to think about it, the connotation. It's not the definition. But math before calculus was very static. There were only so many types of problems that you could solve. And so math does apply up to this point in some different ways, as far as like arithmetic can be helpful in calculating tip at a restaurant, or in making sure you get the correct change, or in doing recipes, yeah, of course. And there are much broader applications to that as well, in the sense of having the idea of an unknown and being able to quantify that and put it in a formula and be able to take clues about what's going on and find the unknown. That's what all of algebra is kind of based upon. Geometry, of course, when you're dealing with shapes, then you can think of construction, you can think of carpentry, of architecture. You can think of other things as well. Is almost anything man-made has some sort of geometric basic figure to it. But then you start thinking about glass blowing and bases and working with wood on a lathe, etc. When you get much more exciting shapes than just the regular geometric ones you guys know they think. But geometry has lots of applications as well, with if-then statements and logic, how to think through argumentation and how to think through proving what you're saying and why you're saying it and having a sound basis to it. We want to be a logical people, that's true. Hopefully we bring that logic under the authority of the word. That's where I find my truth. And so even though logic is important and reason is important, I still believe that as a result of the fall, not only is my heart deceitful and desperately wicked and can know it, but also my mind is falling. So even though there are great minds out there, they still need to be brought into submission and into submission to what I hold as my truth, which is the word. Really interesting, like blog there on that. But anyway, some article in the local. But anyway, our thinking, I would say, is also falling. But we do try to develop your logic in math and have critical thinking, problem solving, etc. But only when calculus comes can we start dealing with some of the real world problems in things such as physics and chemistry and in even some of the medical imaging. A lot of the advances in technology. And that can go into like CGI, different things in the arts as far as what's been possible with graphic design, et cetera, and the programming that made that. Even coming down to the video games you guys play. They would not be near as realistic if fractals were never applied. If fractals were never applied. Don't really look at fractals specifically right now today. Let me see if I can actually get this back to the Calculus also has a lot to do these days in the field of economics. There was an econ professor from USC, he's retired now, he goes to my church. Actually can't come to the church anymore, he's not at this point. But he was like, you have no, basically like it would blow my mind how much calculus is coming to the field of economics. I never needed to learn calculus when I was going to high school with Kaplan. The field has made leaps and bounds as a result of calculus. So calculus is behind a lot of these different fields and behind advances in a lot of these different fields. And this is just totally really sad and not working. So let's just come back to the smartboard notes and stuff. But I'm not going to necessarily be able to show you all that today. That's not necessarily even my goal to show you all of that, or even the huge debate that calculus was back in the day when it first started becoming a thing. How one guy was like, hey, look, I figured it out. And like presented it to the world, and this other guy was like, yeah, good job. I did this a few years ago, and you're kind of wrong, so now I have to come out and say that I actually invented it, and you're wrong about this and this and this. Anyway, there's this whole debate, and back then they didn't have all this hormones and you did debate about, or pop culture, or movie stars. These people who were figuring out things and inventing was this huge debate about whether it was live text or whether it was Newton, who was right, and all this stuff. This big old smear campaign. And then it took off after that. My goal is just to give you a few little concrete ideas about what calculus can do, to kind of introduce the two big problems, once again, that it's built on, in the sense of not necessarily what were the specific problems that these guys were trying to figure out as to how they came about and said, oh, hey, this will answer our question, because they were specific applications, but kind of what calculus got narrowed down to as in it really answers this question and that question, and then we'll kind of just scratch the surface of the introductory stuff as far as the one big thing, the one big tool that makes all of calculus possible. So, technically, without calculus at all, we'd be able to plug in x equals c to a function and say, hey, there's a point. But without calculus, we would have never been able to figure out you would never been able to figure out the limit as f of x approaches, the limit of a function as x approaches c. And you guys are like, but we found poles before. Yeah, but you're given like a dumbed down strategy. You weren't necessarily given a theory behind it. Without calculus, we could figure out the slope between two lines. So we could figure out for a linear rate, a constant rate, we could figure out that constant rate. But as soon as rates start varying, as soon as we have curves, as soon as we have amounts that are increasing or decreasing by varying amounts, we wouldn't be able to figure out those rates. Rates at instance is what we call. Oh, it's down here as well. We could figure out a line that goes through a curve, but we wouldn't be able to figure out the line that skims the curve. And some of your physics might be able to think about, for instance, if you were like a discus? Is that what it is? In calculus?
Yeah, I think
yeah.
it is.
Is it disc or discus?
It's
okay.
both ways.
If you were to do that, right, it might be interesting to know what the speed is as you release in order to try to think about what your maximum potential is as to how far you can throw it, et cetera, et cetera, et cetera. This, you wouldn't be able to kind of do like an average thing. You'd be like, yeah, that's a approximation. But you wouldn't know for sure how fast you're actually releasing at the instant of which you let go. Average rate versus instantaneous rate. Before, we could figure average rate. On average, what's going on as you go from point A to point B. But what's happening at each and every instant only is possible with calculus. Before, we could figure out, I think the pre is on the left and then the after is on the right. Or the without is on the left, the with is on the right. Curvature of a circle is possible without. The curvature of any other sort of curve besides a circle is impossible without. Height of a curve, we could do that. Height of a curve at a point, we could do that without. That's similar to plugging in. But finding a maximum, some of you guys like that feature on your calculator. That'd be totally impossible if it wasn't for calculus. Finding the highest in between two points. Think back to geometry. We worked a lot with circles and with, I guess, kind of spheres, because that can be applied in a three-dimensional realm as well. If you could still only work with spheres, you wouldn't have been able to go to any other sort of curved surface. We could figure out direction of motion that only goes in a straight line, but we couldn't figure out direction of motion along a curve. Kind of goes back to the slope of the tangent secant line thing. Without calculus, sure, we could do rectangles and triangles and circles, and those were all discovered in different ways. But we would have never been able to figure out area of some other figure that could be under some sort of curve, some sort of non-geometric figure. Let's look at trapezoid that it's actually not. We could do constant force, but not varying force. We could do the center of some sort of rectangle or other geometric figure, but we couldn't find the center of any other sort of region. We could find the length of a line segment, but not the length of the arc, without having it be something like string that you could cut and then lengthen the line. And that gets into the third dimensional realm. But yes, we could work with all the things you guys have seen before, the cylinders and the rectangular prisms and all of those sorts of shapes. So we wouldn't be able to actually deal with the volume or the mass or the surface area of other unique figures that might appear or might be used or might be needed. We wouldn't be able to be precise with those figures without calculus. We could have only stuck to the basic ones of geometry. And then it comes into sequences and series. That's actually calculus 2, calculus BC. But a lot of things that you guys saw, polar and parametric, sequences and series, partial fractions, even to some extent conic sections, those come back in calculus 2. So even if you take calc 1 or calculus B, they're like, well, pre-cal, what was the point of that? Remember, it's pre-future maths, pre-physics, pre-calculus 1, 2, 3, we get kind of 4, 5, 6. Pre-linear algebra, pre-statistics kind of in some ways with probability, pre-computer programming, pre-all sorts of other types of things. But specifically in calculus, we would kind of stop at least for calculus 1 level, and say, all right, we'll see some of these things. Not in tons of depth, because some of these are much more physics with the varying forces and the masses and the densities, et cetera, et cetera, et cetera. But these are just like the actual mapping, not very field-specific types of questions that calculus can answer. And yet I say that calculus comes back to two main problems. Calculus and all of its different applications and all these different fields that many people have benefited from the advances that were made possible partially through calculus and partially with technology, of course, but maybe calculus and other maths applied to technology. At the foundation of calculus are two questions. One's called a tangent line problem. You're going to see this page and next page, and the other one's called an area problem. You guys kind of saw different things about this. We saw this when we were doing parabolas. I didn't test them on it, because calculus makes it a lot nicer. And a parabola one only works for a parabola. Is I'm like, that's not very good. Math is better the more generally it can be applied. The broader the truth, the more applicable. The more confusing it can be. Kind of like scripture, how there is lots of truth in it, but it's not necessarily specific about everything. Principles that some specific things. Caleb, what's your question?
On the last slide, it said something about like variable density. What does that mean?
It's like if you have multiple densities across the system. So it's like a mixture.
It depends on the type of liquid or the type of material that you're dealing with as well, as to what that might look like. Especially if you have maybe like a mixture of different types. So you could have varying densities as opposed to one constant density, which could definitely affect how material in that medium would react or would change. So tangent line problem. Long story short, you guys saw tangents in geometry. We kind of talked about it when we did the whole quadratic thing, right? You guys saw tangents in geometry, but they were only tangents to what? Oh, in geometry though. They weren't even parallels. That was only this year. You guys were scared of it. What was it? Circles. You only saw tangents to circles. Got the idea of a tangent, but only if something was moving in like a circular pattern. But the dilemma comes if we're trying to find a tangent line, which can be applied to, remember, slopes or rates. And so an instantaneous rate is actually just an application, one type of application of a tangent line. We're trying to find a tangent line to a non-circle, and even more specifically to a non-parabola. So if I were you guys, since we have seen the parabola one, because there is a way of doing that with foci, I want you guys to make that a non-parabola. How could you do that? Because it looks kind of parabolic right now, right?
Maybe top curve downwards.
Yeah, make the top curve downwards. You can have that. It could be like some sort of backwards and extended transformed cubic. You could have this side go down. You could have it do something really weird and have it do like some sort of leveling off. Just make it a non-parabola just for sake of argument. Let me try it. But somehow extend this to make it a non-parabola, because as we see in the parabola, there is a way with the focus that we could go ahead and think about parabolas and tangent lines to parabolas. The majority of calculus is that it extends our reach. It extends our reach. It doesn't just limit us to what was possible with geometry, whereas the old mathematicians would say with a straight edge. The straight edge man. What else would this say? Straight edge man.
A calculator.
No.
A computer.
I just did a straight edge.
Just spell.
Maybe it was. Okay, so dilemma. If we're trying to find a line, kiddos, how do we find a line? Think about the equation of a line. What's the type of equation of a line that I always like? Point slope. What do you need in order to make a line? 2 points and a slope. Wait, why 2 points? I thought just 1 point and a slope. Why do we need 2? to make a line, to graph a line. Okay, to make a line and to graph a line, yeah. But also, we need 2 points in order to solve for the second part that we need, which is a slope, right? The only definition that we have, the only formula that we have for slope is rise over run. And to get rise over run, we need y2 minus y1 over x2 minus x1. Let me go ahead and show you that pictorially. Here we go. With Precalc, the dilemma is that we would need to somehow identify 2 points. So if we do want the point, I shouldn't say the point, the line at one point that skims the curve. Tons of applications to that, but the line that skims the curve at one point. If we wanted that, it's like, well, we can't just use 1 point. And this is kind of a zoomed in version, because if you're thinking if we are going to use 2 points, we would probably use 2 that are very, very close to each other. And say, okay, hopefully that's going to be approximate to the tangent line. But just to show you the idea, we can only work in Precalc with 2 points that are separated from each other. The problem is, this looks a whole lot harder than just like a find the slope between 2 points problem, right? The reason being is because this is very generalized in that it's saying, okay, between any 2 arbitrary points, there is a delta x, there is some sort of change of x, and that's what you guys see demonstrated up here. There is a delta x or a change in x between those 2 points. There's also a delta y, which this looks a whole lot more complicated than a delta y, but hold on. What's this nasty spiffy name for y in function notation? F of x. So what do you guys see? Change in means subtraction. What kinds of values are these if they're f ofs?
So that's nice.
Yeah. So this is our delta x. These are our delta y's. We have y2, f of. We have a y here, and f of. We have a y here. Now, this y would be the y2 of the point P. So if we have a c, if we have an x value, we have an f of c or a y value. And then, given 1 point, we're building off of 1 point. If we move a distance away from that point, which we would say is delta x. So we move a distance away from c, that's the new x value. Then we have to go ahead and instead of plugging in c, we would plug in the new x value, which is c plus the distance removed. So all this is just kind of generalizing and saying, whatever, you got 2 points. So this all comes back to before calc, without calc. Yes, you could find the distance between 2 points. Yes, you could find the y2 minus y1 all over x2 minus x1. And more specifically, applied to this general notation, you would take the y2, which would be f of c plus delta x, minus the y1, which would be f of c, all over c plus delta x minus c. Long story short, that just ends up becoming delta x alone. And some of you might be like, hey, there was this thing called the difference quotient in first semester. That looked kind of like this. We were just seeing if we could plug and chug back then. Can you plug and chug? Can you plug into a function and with really yucky stuff and simplify? But now it's actually starting to get applied. So, before calc, we could find the slope between 2 points. Yay! But with calc, we're like, we're not just trying to get an average. We're not just trying to get between 2 points. We want an instantaneous. And so an instantaneous, aka a tangent line, in order to get, I get my marker to select. In order to get that tangent line, in order to get to that tangent line, we say, all right, let's take that point that is pretty removed, and let's just make it less removed, and less removed, and less removed, and hey, while we're at it, let's just make it less removed, and less removed, and less removed. And as you get it less and less and less and less and less removed, kiddos, what's going on to each of these lines that were pretty far off of the tangent line? What's going on as we keep on going in? Getting closer and closer and closer, getting warmer and warmer and warmer. That's right, to the real one, to the one that we're trying to find. And calculus says, okay, even though we can't find the slope given just 1 point, because if we were to get the slope of just 1 point, we would have a y1 minus y1. There is no y2. And x1 minus x1. Normally we'd say 0 over 0. That does not exist. It's impossible. But calculus says, actually, 0 over 0, I can work with that. I can work with that. And it all comes back to this thing called, we need to figure out what the secant lines are converging to, are approaching. Two words I've used before. Converging to or approaching. And we're going to use what's called a limit. The second big problem upon which a lot of calculus can kind of be categorized is called the area problem. There are ways of figuring out with the straight edge and the compass, the foundational geometry, how to find areas of circles, rectangles, squares, trapezoids, triangles, surface area of cylinders, rectangular pyramids, triangular prisms, cones, all these things you did in geometry. As soon as the figures get a bit more complicated, geometry wasn't enough. Now, could we possibly fit in some geometric figures and say, well, there's, a rectangle, that covers a lot of it. And maybe we can throw in a circle, that covers a lot more. Maybe we can do a triangle, but even all of that, guys, wouldn't that just be, in some ways, shapes or forms, approximations, right?
Yeah. I think it's approximation.
Right? You could fit stuff in and say, that's close. And how could you make it even better?
You could
Zoom in and fit in more, right?
Yeah.
Zoom in and fit in even.
do it.
Put a trapezoid.
Eventually, you would be off.
But at some point you would be off. That wouldn't be very precise. And if you think about different fields and how they're applied, sometimes the slightest error could make or have a huge consequence. So the dilemma was, how do we find the area under something that is curved, that is not one of those perfect geometric figures from the past? And even technically, maybe those geometric area and volume and whatnot formulas maybe come back to calculus too. Interesting. I mean, also. Not as interesting. So, what I kind of showed you, there is a way to approximate with non-calculus techniques. In order just to be systematic, in order just to have a set approach, we go ahead and say the best way to approximate is using rectangles. Yes, you can fit in more shapes, but the problem is that would be dependent on what type of curve you have. And once again, there is a lot of value in being able to generalize a solving procedure. So we could estimate specifically with rectangles, and you could draw rectangles from the axis up to a function. And if you guys notice, each of these stop, hit the function, kind of like an inscribed shape. Each of these hit the function at different points at different y values. And we can actually figure out things like, hey, we can figure out that the base of each of these would be changes in x, where you take b minus a, you split it into however many rectangles you want to make. That way we can make these even bases. And then you can figure out the heights by using different y values, different function values at each of the different x's. I'm not going to go into tons of depth of this. But you could go ahead and figure out the heights with y values, and so you can multiply delta x values by delta y values, bases times heights. You can add them all up without an approximation. But how could you get a better approximation? Not by adding more shapes, we're saying just rectangles. How about by including more rectangles? How about by including more rectangles? So instead of just fitting in 4, how about fitting in 8? And it's hard to show you guys necessarily right now the calculus of it, so let me go ahead and open up this Wolfram Alpha document I have that'll help us a little bit more.
When's our test on chapter 12?
Good question. But as we go ahead and go,
Well,
It's okay, Ricky.
recording? So we did for
Are you gonna take notes?
No, I'm not.
No.
She recorded.
if it opens, sadly now it's not opening.
But the recording is correctly.
I do too.
It's trying.
Fun logo.
It's a fun logo, I agree. Now it's opening the welcome screen. That's exciting. The idea is going from 4 to 8 gets these rectangles even closer to the curve, and to make it an even better approximation, why not let's fit in 16? To make it an even better approximation, why not let's go ahead and fit in even more? Now this is going to be a little different. We can make this a little bit more fun. What would be a fun one, like sine of x? That's kind of boring, but it's a little bit more similar to what we have. The cubed would be a little better. No, that's not going to work. Exponential function. Whatever one we use. Here's the long story short. You guys just see 4 rectangles, right? But can you guys tell that all of this that's not being covered is going to be the error, is going to be how far off that approximation is? So instead, let's maybe add a few more rectangles. Maybe a few more, and a few more, and a few more, and a few more. Now, the problem is there still error?
Of course.
Yeah. But question, what's happening to that error?
It's decreasing.
It's decreasing. Now you can imagine how tedious it's going to be to literally go ahead and split a function into 40 subintervals and find 40 of the different areas, which is why, well, okay, thank goodness, calculus isn't necessarily splitting up into 40 and then 100 and then 400 and then 4 million. Different little rectangles underneath here, but if you think about it, as we fit in more and more and more rectangles, the bases get smaller and smaller and smaller, and the error gets smaller and smaller and smaller. And if there was a way to fit in infinitely many that are infinitesimally thin, and instead of actually having depth to each of these rectangles, which produces the error, because as soon as it comes out, it's going to be a little bit off the curve. If we could theoretically accumulate second-dimensional slices instead of third-dimensional rectangles, well, maybe that would be possible. But the dilemma is, the second-dimensional slices have area. Does a line have area?
No.
It has to go out somehow. So calculus resolves that problem and says, hey, how do we fit in infinitely many rectangles, mathematically speaking, and not have to actually do all this annoying by hand work of adding up the rectangles? Anyway, let's come on back. So this picture is an example of what calculus does. It says, hey, let's split it up smaller, but it would go much farther, and let's say let's split it up smaller and smaller and smaller, kind of like what you just saw over there. But once again, you would need some sort of limit to say, well, we can't really do it by hand ourselves. If there was a way that we could make the math do it for us, then maybe we could converge, we could approach the actual area. All of that comes back to, I want you guys to write it down. It would have been nice if we written down the tangent line problem and the area problem. As the two big problems of calculus, it might come up at some point. We didn't necessarily have to get down a lot of the before calculus and the after calculus. But the long story short of it, guys, is for the two foundational problems, leave limits. You heard me say converges. You heard me say approaches. That type of math all comes back to limits. It wasn't called limits originally. It was called the idea of infinitesimals. The two different guys I talked about had two different ways of talking about it, two different ways of noting it. There were these monks that got all mad and said, hey, you're trying to say that from nothing comes something. Funny that they would say and get mad about that. There was a whole debate about it, theological debate.
When was that?
2004.
1700s? But the questions have been around much longer. These was the two guys. Newton did a lot of the groundwork, but Leibniz isn't to be discounted because he did actually help a lot with notation, making it more practical for the actual use. Anyway, what to say? Why did I cover all that? Because it says why we're talking about limits.
Wait, so that was
Talks about why we're talking
Oh,
about limits.
is this like the official start of chapter 12?
This is 12.1. The other one was 12.0 or 12.p is there.
This is issue 0.
Yes, I
There's
want to
three
put them in your table of contents in the front.
things.
No, you don't have to have all those figures that I showed you that I looked like. The beginning that I had you write down the tangent line area problem being the two big foundational problems in calculus. And how calculus is a limits machine. It's a machine that is run on limits. Now we have alternative power sources these days. Just think about the different possible alternative power sources. Most machines run on something.
You do?
Yeah. Calculus runs on limits. We're going to start very wordy, and then we're going to kind of take away the words and get to notations. We're going to start pretty wordy. Hopefully get into our calculator. Limits can be seen basically 3 different ways. I guess there's a 4th in the verbal description. Like all of math, the big rule of 4 can be seen numerically with tables, graphically, all graphs, algebraically, analytically, I guess we could say, with equations or functions, and of course, verbally kind of encapsulates them all. This is very informal. I'll give you the formal definition. You need scared, and don't worry, the formal definition is not necessarily required, at least as far as the high school education is. I'm just giving you an introduction to what's to come. Maybe not even what's to come, but just the feel. Okay, f of x. As you guys are writing, I'm going to try to identify some of the key players over here. There's f of x and L, they're related. And then there's x and a. As you guys are writing, there are 4 key players. We have a function, and somehow he's becoming arbitrarily close to a single number L. And then you have x, who's coming arbitrarily close, approaching a from either side. Technically, I guess I should say from both sides, but I'm saying from either side, whichever side you come from, they need to agree. If the first statement is true, f of x is becoming arbitrarily close to a single number L as x approaches a from either side, then the limit of f of x as x approaches a exists, and the limit is L. The limit exists, and the limit is L. So the girl fan is just hanging on, we're getting to the DNA part.
So not an aspect, because that doesn't reach. That doesn't actually reach.
Right, but not quite for the reason that you're thinking. A limit doesn't truly depend on what's going on at the point. It's more about the approach. So a limit at a whole will exist. A limit at an aspect will not. So really quickly, if you guys notice, if f of x is becoming close to a single L, then they must be the same type of value. And by type of value, I mean a y value, a function value. So L, the answer to the limit problem, if the limit exists, is a y value. If x is approaching a, then they must be similar values, aka they must be x values. I meant that plural because I'm talking about 2 different things. And f of x is a y value, or a function, a set of function values, a function based upon x's that produce y values. So L is a y value, A is an x value. And that's the wordy part. Let me go ahead and try to take away some of the words. Take away some of the words, we would then go ahead and kind of progress to down here, where I say the limit of f of x as x, we've learned this one, right? What's that taking the place of? Approaches. As x approaches a is L. Or another way of saying it, and once again, all this is dependent on the limit existing. But we can say the function approaches L as x approaches a. So the nice thing is, some things that we covered earlier this year with the arrow is kind of coming back in the sense of, hey, it shortens this big old wordy, informal, not even formal definition of flow as to what a limit is talking about. Once again, a limit is all about the approach. And the nice thing is we can actually go one step further and get to our notation. And our notation, we can say, what is up above the limit of f of x as x approaches a is L, is what I've shown with notation down below. And we kind of saw this just for a little itty bitty tiny bit when we were talking about the sums of infinite geometric sequences. Because we were saying as long as the common ratio is in between -1 and 1, not including -1 or 1, as we accumulate or as we add bigger and bigger terms, the terms get smaller and smaller. And as I demonstrated with my podium, as I take smaller and smaller steps towards that finite sum, it's still going to converge, even though there will be infinite additions. Anyway, that was just the idea of sometimes infinitely many steps can still converge or approach a finite amount. So LIM stands for what? Limit. Who's the main guy that we're talking about of the function f of x? what's going on that we need to be paying attention to? X is approaching A. And what are we looking for as an answer? So, the paragraph is pretty daunting, or probably still is pretty daunting. The words in the middle may be a little bit easier, but still a little scary. At the bottom of the page, this is what we're seeking to answer. For a given function, as x approaches a given constant, and we'll actually expand that to even infinities, is there a limit? Will the limit exist? Now, I'll look at this page a little bit more tomorrow. You guys don't necessarily need to write this down, but maybe some other ideas of trying to show some different ideas, illustrating limits. But we're going to basically end here. I'll get back to that page a little more tomorrow. You guys have fun in there. I said there are three main ways of solving limits. The first way numerically, using a table. The first way is numerically, using a table. Examining values of f of x as x becomes closer and closer to the number it's approaching, which we talked about on the page before. You guys figure out what letter we represent the number that x is approaching?
A.
So specifically what I'm talking about is A. And as you guys are writing that, let me go ahead and show you basically the setup of how we're going to be using a table to solve. This is the experimental approach. But since A is an x value, I can spell below. We put the x value in the middle. And we're asking ourselves, as x comes towards A, from below and from above, and we're really cluing in, concerned with, focusing on the little narrow window around A as we're getting really close to A. Not really caring so much what's going on far away from A. We're asking ourselves the question, from below and from above as x approaches A, is y approaching L? If the y's are approaching the exact same constant, we say the limit exists and the limit is L. We don't even necessarily care about what's going on at A. Sometimes it's the same thing as L, sometimes it's something totally different. We're not even necessarily concerned about what's going on at A. What we're concerned about is the approach. Asking ourselves, does the limit exist? Alright, kiddos, tomorrow make sure to have your graphing calculators. I was off to with them. There's no other ones that we're missing. You need them tomorrow, Monday, as we solve. If you want your homework spirals, they should be done by the end of the day.
Have a great day, Mr. Lewis.
You guys too.